Recordings rolling. It's Monday, November 17th. Okay, so first, don't worry about AP. I'm doing a Kahoot with you guys. So a bunch of conceptual type questions. I'll do a quick review with you guys. This is going to be on momentum. You guys remember momentum is mass times velocity. This is a vector value. It's conserved in closed systems, and you apply it to collision physics. Right, so hang on to that idea. Do a review. We'll do a Kahoot. All right, later this week. Okay, probably pull some more textbook puzzles at some point. I got one or two more labs that I could do with you guys. Oh, I do want to get you guys a take-home quiz by the end of today. So last couple minutes today, I'll hand you guys your next take-home quiz, which is way earlier than I usually give it to you guys. Now, guys, this is going to be due for a long time, but I want to give it to you guys with plenty of time because, well, if you finish it in the next few days, then you don't have to worry about it at all over Thanksgiving break, okay? Which I think you guys might be able to do. Okay. I've been giving you guys a lot of take-home quizzes for a few reasons. One reason is that I like to ask you guys some complex questions that it might take more than a class period to answer 10 questions. Okay? But here, I do want to fit in an in-class quiz in early December, so not the first day back. I'll probably do a little review with you guys. This is going to be on energy and momentum, so the questions will be a little bit simpler than the ones I normally give to you guys, so that you can reasonably finish this in class. Right, but just to be thinking ahead a little bit. So uh, early December, so maybe a few days after you guys come back, I'll get you guys an in-class quiz. So, any questions about anything going on agenda-wise? All right, so let's just review here. So I remember momentum is product of mass and velocity. It's a vector value, which means that if you have two objects headed opposite direction, guys, could you have a positive momentum and a negative momentum? Yeah. Right. Could you even set this up in such a way that there's zero momentum in the system? If this guy's moving slowly to the right and the smaller guy's moving very quickly to the left, there might be possibly zero momentum in the system, right? Right. So that could be, right? And then anytime you see a collision, you think in this framework, right? So here, I got a few of my main posters here. Here's conservation momentum. So here's a collision. If you add up all the momentum bits before and after the collision, the momentum has to equate for a closed system. Okay. Now, guys, is this look at this picture? Is this a positive momentum and a negative momentum? Yeah, it sure is. Maybe it's like positive 12 units and negative 10 units. Okay. Because what if you had that? What if you had positive 12 and negative 10? What's the total momentum in the system?
Positive what?
Positive 12 and negative 10 makes what?
22. Or
Positive.
this is two.
Two. Yeah, 2 units of momentum. Right? So after the collision, there still have to be 2 units altogether. Right? What if you have uh, positive 3 to the right? What do you have to the left? How about 1 unit to the left? So that 3 plus negative 1 also brings you to 2, right? Couldn't that conserve momentum? Right? Depends what kind of collision. Now, there's a whole spectrum of collisions. We're going to address that later this week with coefficient restitution. Like, what if you have two half-inflated tennis balls or something, right? But at one extreme, the two objects could stick together, right? And that would be perfectly inelastic, where they combine to make one giant mass moving at some common final velocity. You could have that, right? Could have that, right? And at the other extreme, you have what's called perfectly elastic. Right. And a good example is Newton's cradle, right? These balls are like super bouncy. So if you get super bouncy balls, boing, 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 right? That's probably about as close as you can get to perfectly elastic. Okay? And then in terms of the physics, what's conserved is not only the momentum, but also the kinetic energy. And then this gold box here always gives you that solution, right? I do not expect you guys to memorize this or not so much, but maybe just be aware of the big picture of how that works, right? So this system of equations, right? Like maybe kind of know that this system exists for this type of collision. Okay. If we have time later today, I do want to solve one of these with you guys. And this is also going to show up on your take-home quiz, this ballistic pendulum. So you fire a bullet into a pendulum and it swings up to some height. Now, there's different questions you can ask, but the classic question is usually how fast was the bullet fired? So you solve this backward in time, say, well, if I know if it swings up to some height, I can use conservation of energy to figure out how fast this whole system was going at the bottom. And then I can step back in time and say, well, collision physics, this bullet did collide with the block. So then I can step back and figure out what was the firing speed of the bullet. Okay. So yeah, if we have time today, I'll do one of those with you guys. Okay. Another big important concept is impulse, which is a change in momentum. That's what delta P is, right? Change in momentum. Okay. You get that by applying a force for a time interval. Okay. I remember about 3 weeks ago, remember work was force times distance. Okay. Now we have impulse as force times time. Okay. Similar concept, different units. Okay. So deal with collisions there. Okay. All right. So those are some of the main posters you guys saw last week. All right. So you guys ready for Kahoot? Kahoot. Kahoot time. Let's see. Oh yeah. You guys On here, ready to go. All right, the pin is still on the board if you're still going to be hopping in. All right, so 20 questions on momentum. The momentum of an object is defined as. Yeah, mass times velocity. There you go, mass times velocity. Uh, what are these other things? Okay. Guys, what is velocity times time? That tells you what starts with the D. Dis displacement. Aha. Okay. If you go like 60 miles an hour for 3 hours, you've driven 180 miles. You guys know that. Okay. What is mass times acceleration?
That is force.
Force. Yeah. You guys remember F equals ma? Newton's second law of motion. That's Newton's second law of motion. Okay. And force times acceleration. Well, that's not really anything. All right. So momentum is mass times velocity. Ah, points on the board. Oh yeah. Oh yeah. If the momentum of an object changes, say its mass stays the same. What else is true? Yeah, all those are true statements. Yeah, because momentum's changing and the mass stays the same. Well, that means the velocity is changing. But if the velocity is changing, that means that it must be accelerating because it's an acceleration rate change of velocity. Okay? If it's accelerating, there must be a force acting on it. That's Newton's second law of motion. Yeah, so all those statements would go hand in hand. Right? Is that true? All those. All those. All right. We got 677. Got Gavin, Kai, Cole, Talia. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is what? The same force. Is that Newton's third law of motion? Newton's third law? Okay. Here, good. Draw this out. Is that? Good. Draw this out. So we got this table tennis ball launcher. I'll draw it as a cannon, but you guys get the idea. Okay. And we got this table tennis ball, or you go, you cannonball. Okay. So there's a force acting forward on the ball, and there's a force acting back on the launcher. Okay. And you guys just said it's the same force, which is true because that is Newton's third law. Newton's third law. It's the same force. Now those objects have different masses, so I think the smaller mass would accelerate more, and the large mass would not accelerate not as much. But it's the same force. 6-7, Gavin, Kai, Cole, Talia. Table tennis ball launcher is fired compared to the impulse on the ball. The impulse on the launcher. Ooh, now what? Impulse. Yeah, would also be the same. Here, I want to convince you guys that would be true. Okay. Now, here I'm showing like a single force. If you want to get really complex about it, could you break this down frame by frame with a slow-mo camera and maybe this force varies a little bit? Okay. But let's say the force starts out kind of small. There's some kind of gunpowder explosion here. Okay? Okay. And then the force grows. Right. And then when the ball's leaving, maybe it shrinks again. Okay. Guys, are the magnitudes instant by instant always the same? Forwards on the ball and backwards on the launcher? They are. They are. Right? Even if you have a variable force, like this graph is showing a variable force, right? It's an equal and opposite force back on the other object. Right? So the force on the ball and the force on the launcher would be the same magnitude, just opposite of each other at all times. Right? And the time interval that the force acts on each is also the same. So if it's like 0.03 seconds on the ball, it's also 0.03 seconds back on the launcher. Right? So if I made another graph for if this is the ball and I made a graph for the launcher would just be like the upside down of the force of the ball, but they'd have the same base, right? So they have the same magnitude of impulse, just one's positive, one's negative. Yeah, that's all. And so mass times change in velocity, that product would also be the same for both the ball and the launcher. 6-7, Kai, Cole, Gavin, Talia. Collision is elastic. Ooh, what makes something elastic? Oh. Yeah, I am looking for all the above on that. All the above. Okay. So the only one I explicitly pointed out to you guys was the kinetic energy is conserved. That's the main detail, right? But it does go hand in hand with these other ones because what you'll notice is that if that's true, the objects are always as bouncy as they could possibly be, which would be the opposite of sticking together. Isn't that true? Right? Like if they stuck together, then the kinetic energy is never conserved. Hey, you can show that mathematically. It doesn't matter what numbers you feed in. That's always the case. Okay. Also this too, right? A lot of times my example for an inelastic collision where they do stick together is like two balls of clay. Guys, if you have two balls of clay that stick together, don't they like deform? And in terms of energy, wouldn't a lot of energy go into that deformation? That's actually a huge loss of mechanical energy. It goes into deforming the objects. Okay? But that wasn't true for Newton's cradle balls. With Newton's cradle balls, boing, 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 there was no lasting deformation. Yeah, so all those go hand in hand. Okay, you guys go with the elastic? Elastic. All right, got it. Kyan, Gavin, Talia, Kai, Cole. Oh. Suppose standing on the pond, there's no friction between your feet and the ice. Frozen pond. How do you get off the ice? Yeah, that's the only way. You have to throw something in the opposite direction, or maybe swim against the air, maybe. Uh, but you can't just walk very slowly and attempt it because there's no friction. You guys remember that Magic School Bus clip where they were on the frictionless baseball field? Right, same thing. Like whoever's stuck in the third base position is just stuck there. Right, she was trying to run off the field and cut. I might have that right here. Let's see. I think it's. Let's check this out. Okay. Let's get a picture of this. Look, they're sliding around that field. Right, hits the ball. Oh, there you go. Right, see how she's just stuck. She can't really go anywhere because there's no friction to push against. So she just stuck there. Yeah. You have to throw some the other way. All right, then. All right, Talia, Olivia, Gavin, Kai, Cole. Freight train rolls along a track with considerable momentum. If it were to roll with the same speed but had twice the mass, its momentum would be. That's when you double the mass. Yeah, twice as much. If you double the mass, it'd be twice the momentum. Okay. So that's like here. So momentum is mass times velocity. Right? If you keep the same speed, same d, right? But if you double the mass, see how you're going to overall double the momentum? Is that double? Olivia, Gian, Kai, Gavin, Cole. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because yeah, looking for the cannon has far more mass than the cannonball. Right? How about these other answers? Right? Like, all right, so nobody picked this one. The momentum of the cannon is unchanged. Okay, so that wouldn't be true, right? Because it does have a force for some time interval. There is an impulse on it. Right? The force against the cannon is relatively small. Well, the force is the same in magnitude as against the cannonball. Right? Remember, from Newton's third law, the forces have to be the same. So it's not that there's a small force necessarily. Right? Impulse on the cannon is different than the cannonball. No, again, impulse is also the same. You guys saw that question earlier. Right? So if we go back to, oops, okay, go back to this figure. So there's an equal and opposite force. It's the same force on the cannonball as uh, back on the cannon. Right? Also for the same time interval. Right? So same force for the same time. They're getting the same impulse. Right? Impulse on the cannonball is right equals impulse on the cannon to the left. Right? But here, if I write some number, here I'll write it this way. Right? A small mass times a large change in velocity is equivalent to a large mass cannon times a small change of velocity. This is the same impulse. Here, throw some numbers. Okay. So if the mass of the cannon was like 200 kilograms at 1 meter per second, that could be equivalent to say like um, let's go with 2 kilogram ball going at 100 meters per second. Okay. Just throw some numbers in there. All right, Olivia, Gian, Gavin, Ty, Cole. In order to catch a ball, a baseball player moves his hand backward in the direction of the ball's motion. Doing this reduces the force of impact. True. Why? Uh, yeah, so it's that the time of impact is increased. Now, the impulse actually stays the same. Show you guys why here. The impulse stays the same. So, all right, so we're looking at here you go. Impulse. Right. So impulse, change of momentum. Right. You get maximum change of velocity or force times time. Right. Hey, guys, can I rearrange this? And if the target question was something about it reduces the force, because maybe we could solve for force here. Can you do that? Right. So can I say force, like an average force equals, right? Well, wouldn't it be m delta v divided by delta t? You see it? Right. So mass times change in velocity over the time interval, something like that. Right? Yeah, let's throw in some numbers. Okay. Let's say somebody brings this to a sudden stop. So I got a 0.15 kilogram baseball. Okay. Let's say it's going like 30 meters per second, and then it goes to zero. Guys, from 30 to zero, wouldn't the change be 30? Right? Or negative 30, whatever. Let's drop the negative. Right? Now, let's say this person brings it to a really sudden stop, like 0.01 seconds, just really, really fast. Wonder what that force is. Let's find out. It's 30 over 0.1. Great. Look at that, 450 newtons. Now, it lasts for a really small time, but it would be a huge force, wouldn't it? Right? And what if you take the exact same baseball, so 0.15 kilograms, also throw in at 30 meters per second, and you're still bringing it to a stop, so the change of velocity would be the same, right? From 30 down to zero. Right? But you pull your hand back while you're catching it. What if you sort of like triple the amount of time it takes for it to a stop? You see that triple the amount of time? Yeah. Well, I should get a third of the force. Yeah, 150 newtons. Right now it's not nearly as much force. You see that? Right there. Okay. How about this? Here's a similar principle. You guys hear that? Those numbers? Okay. Here's a similar idea. Okay. What if there's a building and you're up on the third floor and this building's on fire? Okay. You got to get out. And the only way is you got to jump. Okay. And you look down and here's the sidewalk below. Okay. And if you jump just right, you might be able to land on this trampoline. Or that, or you could fall and you could hit the sidewalk. Right. So would you rather land on the trampoline or on the sidewalk? No, the trampoline, right? But what changes? Yeah, probably most of us. Let's go with the trampoline, right? But what changes in terms of those physics, right? Well, your mass is the same. The change in velocity would also be the same because you built up some speed by following this distance, and you're going to the speed of zero. So m is the same, delta v is also the same. But the advantage of the trampoline is that it extends the time interval of that stopping, right? It might be like a fraction of a second, right? But it's better than hitting the sidewalk where you come to a stop all at once. Okay? So yeah, if you can extend the time of stopping, then that will decrease the force. Yeah, Talia, Gian, Gavin, Kai, Cole. That car traveling along the highway needs a certain amount of force exerted on it to stop, right? More stopping force could be required when the car has what? Yeah, all the above, right? So if it's 3 times the mass, I bet that would require 3 times the force to stop, right? If it has more momentum, same thing. That could come from the mass or the velocity, but it would take, right? Also, if you have to stop that car in a hurry, like short stopping distance, yeah, you would need a greater frictional force for that. So yeah, all those could be true. All the above. 6-7. Gian, Kai, Cole, Gavin. Force of an apple hitting the ground. Ooh. Okay. Yeah, it depends on all those things. Okay. What's the speed of the apple it's about to hit? The greater the speed, the more force it would take to pretty much stop. Time of impact with the ground, and also whether or not it bounces. Yeah, all those would be true. So let me convince you guys that all those would be true. Okay. So it has to do with this impulse formula right here. Okay. So I know change in momentum could be mass times change in velocity, which is also a force applied for a time interval. Right, so it's just straight off this poster, right? So just copy that right there. Okay, got that. Right. Now, how does it apply to an apple falling from a tree? Well, let's get an apple tree going. So here's my apple tree. Okay. And then what if I have a scale down here? And the scale is going to read a force. Isn't that what a scale can do? Like a bathroom scale can read the force? Right, so here comes the apple, it falls and either like splats and hits, or maybe it rebounds, boing, and bounces off. Right, right. And that could make a difference too, right? Right. So let's read the music of these equations here. So I'm solving for this force right here. This force. So the force is really like an average net force is what we're talking about. Okay. Could be the mass of the apple times its change in velocity over the time interval, delta t's time interval. Is that true? Right? Now, the mass of the apple is the same regardless. That doesn't matter. Right? But I think here, if the apple fell a further distance, like a greater height, wouldn't it be falling faster, faster, faster? And so you get a greater speed down here. Okay. Right. So okay, so that would have something to do with it. Right. They said um, okay, time of impact with the ground. Okay, what if this scale is has a concrete surface? You have a boing, right? Just really small time interval. Okay. Because if you have a small time interval, that corresponds to what kind of force? Small or large? Large, yeah, right. Versus what if there was a cloth covering, so it kind of dampened the fall, maybe it extends it by a factor of three. If you have a larger time, that's a smaller force. Now, finally, does the apple bounce or not? Now, guys, watch this. If the apple sticks, suppose it was falling at like 10 meters per second and it sticks. What would the delta V be for sticking? If it goes from 10 to 0, that'd be what? Would that be a change of 10 meters per second? Okay. But if it bounces, I'll go delta V bounce. Suppose it rebounds boing, at like 7 meters per second the other way. Right? As if it was falling at 10 meters per second and if the boing bounces upwards at 7, what's the difference between 10 down and 7 up? And don't say 3. Huh?
Okay.
10 down, 7 up. What's the difference?
17.
17. Yeah. Because it left the ground upwards at 7 meters per second. It was going 10 down. You're subtracting a negative. Guys, that's 17 meters per second. Do you guys see that? Right? So the delta V of sticking could be some value like 10, right? The delta V of bouncing could be up to twice as much. It might be this right here. It's fairly elastic, right? So if you're pumping up that delta V right there, that could be a greater force. In fact, it might be up to twice the force, couldn't it? Yeah, up to twice the force. There you go. Ooh, that might be a good midterm question. 6-7, Gian, Kai, Gavin, Cole. Um, Moving freight car runs into an identical car, same mass, at rest on a track. The cars coupled together. Compared to the velocity of the first car before the collision, the velocity of the combined cars after the collision. Uh, yeah. Oh, nobody got that. Half as much. Half as much. All right. All right. So if we solve this one, right? And so we've got some car mass m, and identical car means the same mass. Whenever you see the word identical in physics, they're usually referencing same mass. Okay? Now we can make up whatever mass number we want. Here, I'll make it real straightforward. Let's call this guy 1,000 kilograms, and this guy also 1,000 kilograms. Okay? This guy is coming at some velocity. Now it could be anything. All right, let's go. Random number generator. 50. All right, let's say it's coming in at 50 meters per second. Why not? Okay. These cars are going to couple together. That's an inelastic collision, okay, which tells me I want to think in terms of momentum conservation. So sum of momentum before the collision equals sum of momentum after the collision. Okay? And then everything else should just follow. So momentum, of course, is mass times velocity. Okay. So I have 1,000 kilograms car coming in at 50 meters per second. Okay, that's all the momentum in the system. Is that true? Okay. Now, guys, after they couple together, how many guys are thinking this one right here, where they stuck together, they make one giant mass, don't they? Yeah, right. Okay. In fact, since it's the same mass, it's just m plus m. You can call that 2m. Okay. Or since I'm doing numerical example, that'd be 2,000 kilograms. Right? And then v final, and we're solving for this v final. Oh, guys, if I just divide over this combined mass, that's 1,000 over 2,000, and then multiply in the initial velocity of the first car, right? Guess this ratio over here is always going to be half, right? I could pick any mass value. As long as they're the same mass, this ratio is always 1 over 2. So 25 meters per second is the final. Okay. Right? So half. Right? As long as they're the same mass, they couple together. Such. 6, 7, Gian, Kai, Gavin, Cole. Piece of putty moving with 2 units of momentum strikes and sticks to a heavy bowling ball initially at rest. After the putty sticks to the ball, both are set into motion with the combined momentum of. Oh, 2 units, because it was coming in with 2 units. That 2 units is conserved, right? So that's just conservation momentum, right? Now, the overall speed is going to, of course, slow down because we're increasing the mass due to the collision. Okay. Yeah, but the momentum's conserved. 2 units, maybe 2 kilogram meter per second, something like that. Right. All right. How about, I think I got a follow up here. Yeah. Ooh, a bouncy ball. Moving with 2 units of momentum strikes in and bounces off a bowling ball initially rest. After the bounce, the bowling ball is set into motion with the momentum of what? A boing. After the bounce. Yeah, more than 2 units. Okay, let me convince you guys that's true. I have a whole poster for it. It's this one here. Does this one look familiar? Okay. So the first one sticks at represented with the bullet. Right? So it's kind of looks like 2 units of momentum, right? And momentum's conserved. Right? So the whole momentum is just 2 units. Right? But if it bounces off, but when momentum's still conserved, but the outcome is different for each individual object. Okay? Like here, say got this bowling ball. Here comes the bouncy ball with 2 kilogram meter per second, and it bounces off. Boing. Let's say at 1 kilogram meter per second the other way, or you can interpret that as a negative, couldn't you? Like because it's going to the left. Okay. So what's the delta p on this bouncy ball? Would it be -1 -2, which is like 3 kilogram meter per second, right? And that's what's been transferred to the bowling ball because the impulse on the bouncy ball is the same magnitude as the impulse on the bowling ball, right? Or another way to look at this is in terms of momentum conservation. Some momentum before equals sum of momentum after the collision, right? It's just our classic conservation of momentum, right? So there was 2 kilogram meter per second to go around, right? Now, after the bouncy ball boing, bounces off, it itself has -1 kilogram meter per second, because it's rebound. Right? Plus, now the bowling ball needs something to conserve the momentum of the two object system. You guys see the number here has to be 3 kilogram meter per second, because this 3 plus this -1 adds up to the original 2. Is that okay? Okay. That's good. Okay. So if it sticks, it looks like this top picture. If it bounces, boing, looks like this bottom picture. It actually gets the bowling ball rolling faster. Okay. Maybe up to twice as fast. Somewhere about there. More than 2. All right. That would also be a good midterm question. Caitlin, Gavin, Kai, 6-7, Cole. The force that accelerates a rocket into outer space is exerted on the rocket by. Yeah, the exhaust gases. Right? So the gases in the rocket are pushing on each other, right? With equal and opposite forces, equal and opposite impulse, the whole thing. Right? Yeah. All right. Caitlin, Kai, 6-7, Gavin, Cole. Cannonball shot from a long barrel cannon travels faster than one from a short barrel cannon because the cannonball receives a greater. Yeah, impulse, right? Now, it might be an equivalent force, right? Maybe it's the same gunpowder and the same explosion and everything, right? But if it's a long barrel, that force lasts for a longer amount of time. Okay? If I draw this out, let's go short barrel cannon versus like a long barrel. Okay, something like this. Okay? Got right. So some explosion here. It sends the ball. Okay? Okay. But with the short barrel, as soon as the ball leaves the cannon barrel, okay, now it just turns into a projectile. Now it's just going to coast. Okay? Yeah, left with whatever speed be. Okay? Okay. Because if you have a barrel that's way longer, suppose it lasts for like 3 times the amount of time, 3 times the amount of time. Okay? They could it be like 3 times the speed. Okay? So to like 3D, right? And then right? Now it's going even faster, right? Because that force lasts for a greater time, right? Hence a greater impulse. Yeah. All right, Caitlin, Kai, Gavin, 6-7, Cole. 2 kilogram ball thrown at 3 meter per second. What's the momentum? Yeah, 6 kilogram meter per second. Just 2 times 3, right? Mouse and velocity. Guys get it. P equals mv. Just multiply it. All right, Caitlin, Kai, Gavin, 6-7, Cole. 4 kilogram ball has a momentum of 20 kilogram meter per second. What's the speed? Yeah, 5 meter per second. Because 4 kilograms times 5 meters per second brings you up to 20 kilogram meter per second. So P equals mv all over again. Right? Like that. Uh, Ball is moving at 6 meter per second, has a momentum of 24 kilogram meter per second. What's the ball's mass? Ah, yeah, there you go. So 4 times 6 is 24. All right, so everybody got it. P equals mv. All right, so a couple questions to go. We got Kai, 6-7, Gavin, Cole. While roller skating, Granny collides with her tiny grandson Ambrose, who is at rest. Ignoring any friction effects, Ambrose's speed after the collision will be greatest when what? Granny catches them and they move together, or he and Granny have a bouncing collision. Boing. Which one will send Ambrose flying faster? the bouncing collision, the one that's more elastic, is really it's kind of the same thing as this, isn't it? Okay. So if they glide stick together, that'd be like inelastic. Okay. But if they bounce off each other, but more elastic, yeah. Inverse in this case might be more like the bowling ball, so it's fly off faster. Okay. Become faster. All right, got Kyan, Kai, 6-7, Gavin, Cole. We're going for the win. For the win. For the win. If all people, animals, trains, and trucks all over the world begin to walk around towards the east. You guys know the Earth is already spinning towards the east, right? Right, so that's part of the answer. So the Earth is already spinning towards the east. What if everybody on the surface started walking towards the east? The Earth would do what? You know, like the ground beneath everybody's feet. Yeah, the Earth would slow down a little bit while everybody was in motion. Okay, of course, it'd make a tiny, tiny bit. Right, but show you guys. Right? So, right, so the Earth is already spinning west to east. Right? Hence, like if the sun's right here, it would look like the sun was rising in the east and setting in the west. Is what it will look like from the surface of Earth. Right? But if everybody on the surface, right, like all people and animals and trains and cars, started to also walk towards the east, wouldn't they be pushing the ground beneath them towards the west? Right. Now that's in terms of forces, right? Or you could say, like as a closed system, the total angular momentum is conserved. Now we haven't talked about angular momentum yet, but it's just momentum, but in a rotational sense, right? It's still conserved, right? We'll talk about that probably in December, January. Right? Okay. So everybody on the surface walking towards the east is going to cause the Earth itself to kick back a little bit, right? Which won't cause it to fully reverse direction because it's not enough mass, right? But it will slow down a little bit, right? Slow down a little bit, right? Now, what about this? What about when everybody comes to a stop? Will Earth then resume its spin rate just like it was before? Yeah, right. Now maybe it's lagging behind a little bit, right? So, right? But yeah, if everybody comes to rest, then it just goes back spinning how it was. All right. All right, let's find out who won Kahoot. Out with the bronze, Kyan. The silver, Cole. And the gold, Gavin. All right, nice job. All right, so promise you guys I want to do a ballistic pendulum puzzle with you guys. So let's do this. Ballistic pendulum. Right. Um, so let's get this set up. All right, and I'll get you guys here. Take on quiz before you get out here too. All right. Let's have a mass of a block. So M block. Let's call it 2.5 kilograms. Okay. Let's go mass of a bullet. I might just use lowercase n for the bullet. Okay. Let's have it as 0.10 kilograms, 100 grams, which is, I think, this one right here. Yeah. So here's your bullet. Let's have this length of the string be 1.2 meters. And let's have this angle. So, the bullet's going to fire at some velocity, the bullet, which we're solid for, into the block, and the whole thing's going to swing up to some angle. Let's have that angle be 31 degrees. Okay. Now, there's enough information right there where you can solve what was the firing speed of the bullet. You guys get that? And so, are you guys getting that in your notes? Let me dig this out. So there is a connection back to a few weeks ago. You guys remember this for our pendulum? Okay. If you know this length and this angle, that could tell you something to do with the height change. And you want to know that so you can answer the screen box bit right here. So we're going to solve this backwards in time. We're going to say, well, if we went up to some angle change, there must be some height change, h. And that's potential energy that came from kinetic energy of the block being put in motion. After that, we're going to step back in time and say, well, the bullet colliding with the block, how fast does the bullet have to be going so that that can happen? But all I got. Right. So Okay. So solve the energy first. Sum of energy initial equals sum of energy final. Okay. Now, there was some kinetic energy after the bullet embedded in the block. I'll call that 1/2 mv squared. But it's block plus bullet. And so I'll call it V post as in post collision being squared. Okay. Okay. I'm kind of running out of room over here. Well, doesn't that just result in MGH? Okay, so equals, now it is a combined mass because they're stuck together, and then G and then the height change. Is that true? Okay. Now I'm going to rewrite that down here a little prettier. Okay. But I'm going to make a substitution. Equals M plus M G. Okay. Because, do you guys remember from geometry? Now I'm going to get a little short on class time, but do you guys remember you can from geometry solve for this height change as L1 minus cosine theta? Okay. Wait, so I got this triangle here. Here's L cosine theta. Here's L. Here's L minus L cosine theta. You can factor out the L. Looks like that. Boom, boom, boom. Yeah. So in place of this H right here, I'm going to write L1 minus cosine theta. Okay, just like that. No, oops, like that. Okay, now the M plus M combined mass ends up canceling out. Okay, and I'd like to know what's the post-collision velocity, like after the collision. Okay. So I can plug in right here 1.2 meters. Oh, let's go 10 meters per second squared for gravity. Okay, unless it says 9.8, but we'll go 10. Okay, and we'll plug in 31 degrees right here. Okay, all right, so that's 1/2 V post. So V post is, okay, now it'd be taking a square root because this is 1/2 V post squared. So you multiply by 2 and then take the square root. So square root of, I need this factor 2. All right, all the masses cancel. I have 10 meters per second squared for gravity. I have length of 1.2 meters and 1 minus cosine of 31 degrees. Okay. Okay. So this gives you the post collision speed. Not exactly what I'm looking for, but this is an important middle step. So square root of 2, 10, 1, 2, 1 minus cosine 31. Okay. So that is 1.851 meters per second. Okay, you guys get that? Okay. That's how fast this block had to be swinging at the bottom so it could make it up to that height and therefore that angle. Okay. Okay. Now we get to apply conservation momentum. Say, well, what would have set that block going that fast at the bottom of the swing? And that's where we say momentum's conserved. Sum of momentum leading up to the collision equals sum of momentum after the collision. Okay. And it all comes from the bullet. Mass of the bullet times speed of the bullet. Okay. And that's ultimately what we want to know. It's how fast was this bullet headed towards the block. Okay. And it results in the block plus the bullet, right, because inelastic collision, maybe get some final velocity. I'll call it V post. Okay. And now I know all these values because I gave you the mass of the bullet as 0.1 kilograms or 100 grams if you like. The bullet we're solving for. The block I gave you guys was 2.5 kilograms. And now the bullet's embedded in it, so I'll add that too. Okay. And then the post I have right here, this 1.85 meters per second. Okay. And so last algebra step is divide over the mass of the bullet, and I have my answer. 2.5 plus 0.1 times 1.851, all divided by 0.1. Look at it. The firing speed of the bullet is 48 meters per second. Yeah, that looks pretty reasonable. Okay, so something about like that. Okay. All right, so big picture is, right, you solve this backwards chronologically. You say swing up some height, use conservation of energy to figure out the post-collision velocity. Then you say back in time, say, well, the collision got it going that fast, right? And that's from conservation momentum. Okay. All right, so I will put this take-home quiz in your hands. If you finish it by the end of the week, then you don't have to worry about that over the break.